wait until 20 past, then I can? Or can I already start? Oh, we still have some people coming. So yeah, I'll wait a few minutes.
Okay, thank you.
Voice is nice. Okay, for here, people here, okay, for people here, I want you to have your phones. If you have them, you're gonna use them. Or your PC is also fine. Okay, let's start the class. My name is Mito Kokawa, and I'm assistant professor of University of Tsukuba, Life and Environmental Sciences. So I'm going to talk about this topic, food safety control and quality evaluation today. How we're going to measure food quality, basically. Maybe I should close the door. Sorry, there's lots of lines here. Okay, so this class tends to be quite like, I'm talking all the time, you're just listening, you get kind of sleepy. So I want you to, I want to make this class a little bit interactive. So I've set up a site called Slido. So that's what I mean. If you have a PC or you have a smartphone, please search for Slido, Slido, and then you will come to a screen like this. So you can enter the code E746. And then I think you will see a page asking you a few questions. Yeah. Okay. So everyone in the class, have you accessed this event in Slido? So for those of you who came a little bit late, please search for Slido first, Slido. Go to that page and then enter the event code E746. Everyone lost? No one lost? Okay. So when you go to this code, I think you will see one question, I think. Yeah, you will see one question. How many of the following words do you understand? Reflectance, transmittance, scattering, fluorescence. I want you to answer this. And then there's also a link to a Google form. You can click on this link if you can, or you can type in this URL, or you can go through this 2D code. So can you try that? I'm gonna try. Oops. Okay. So here, you guys are answering my questions. You are answering my questions, which are somewhere. All right, I'm gonna. Here they are. For some reason, I cannot share the screen. So right now, you are seeing this poll. Sorry for video people. 皆さんできてますか？できるかな？アメリカ。Yeah, I think we can do this. Okay, yeah, I think we've shared. Okay, so it seems like a lot of people know, well, a lot of people know all of these words, which is very nice. Some people know none of them, which is also okay. Okay, so reflectance, transmittance, scattering, fluorescence, I'm going to talk about them today. So if you know all of them, I hope you get some kind of new knowledge today. If you know none of them, that's also okay. You will learn what they are and how they are used for food quality inspection. Okay. And I want you to go to the second questionnaire, this questionnaire, measurement of food quality. How much would you pay for one apple? And I'm also going to share this. Okay, so actually I've been taking this questionnaire for, I don't know, maybe 4 years now. So that's why I have 59 answers right now. Let's maybe quickly look at these answers. How much would you pay for one apple? So basically, you're not very affluent, probably. You are students, you don't have very much money. Most people, or a quarter of you, would maybe only pay under 80 yen. That's very cheap, right? 80 yen, 100 yen, 120 yen, 150 yen. Maybe there's a difference between students in Taiwan and students in Japan. But yeah, basically, I think for yourself, you want to have something that is cheap, right? You want something that is cheap. So this answer changes when you're gonna buy something as a gift. You're giving the apple to someone. So I don't think, yeah, there's 7.6% who would give an 80 yen apple to someone else, but that's okay. Maybe you have to buy like 10 of them, right? Maybe if you're giving the apple as a gift, you're willing to pay more. Yeah, you can pay a little bit more. So there's no answer for this, but I just want to point out that if you have a different objective, if you're buying for yourself versus buying for someone else, the quality and the cost is kind of different. And okay, what aspects are important when buying an apple for yourself? Of course, price, right? Price and taste, smell, texture. I think those two are the main points. People pay less, they focus less on physical appearance or variety or organic or not. Sorry, this gets updated every time. But if you are giving an apple for a gift, the price is less important. You focus maybe a little bit more on how it looks, physical appearance. Sorry. Every time someone submits, it goes up. But basically, what I want you to notice here that people look more into how the apple looks more than price, maybe. Also, you are focused on the brand or where it has been made, that kind of thing. So these things are different when we buy an apple for ourselves versus when we give it to someone else. Okay, thank you very much for your answers. If I remember, I'll share it with you, share the final answers with you later at the end. Okay, so let's try sharing again. Okay. Come on. And every time I want to close this small window. Okay, sorry, we already did this. Okay, so today I want to talk about how we measure food quality. But before I go into how, I think we should understand why. Yeah, I think there was a very famous book called Start With Why. So why should we measure quality? As we saw right now, we have different objectives or different goals for measuring food quality. The first one you didn't see today, but first reason is we want to separate damaged products from good products. So this I will talk about in the next slide, but please just imagine what would happen if damaged products are left together with undamaged products. That will be a problem. Second objective is we want to separate high quality products from normal ones. Because as you just showed, showed to us, consumers should be able to choose between high quality and maybe high price, and low quality or normal quality and low price. Sometimes you want a low price one, sometimes you need a high quality one. Yeah. So you should be able to choose. And what would happen if this evaluation of quality was unclear or subjective? You pay a lot, but then you get an apple which is not very nice. That's not nice. So we want to have a good evaluation method that will give you clear index on how good this product is. Okay, so 2 reasons for measuring quality. So the first one, separating damaged products from good ones. Why do we have to separate good ones and damaged ones? So there is a proverb in English, one rotten apple spoils the barrel. It means if there's one student in here who is bad, then everyone becomes bad. It means like that, yeah? I'm not talking to you. I'm not talking to you. But yeah, but if you take this word literally, like the word says, it means if there's one box of apple and one apple is bad, for example, you have a small hole in one apple, then the skin of the apple actually is protecting the apple. But if it has one small hole in it, it will begin to rot. There will be microorganisms that grow on it. The rotten area grows, and this will lead to an increase in bacteria, and this is going to influence the other fruits. If you're Japanese, I think in the winter, our grandmother, grandfather, they send us a box of oranges, mikan, right? And you find that when one orange is bad, you find that the whole bag, whole box becomes very bad. So we need to find this apple and take it away before the whole box gets bad. Yeah. So that's why we need to separate damaged products from good ones. We also want to separate high quality products from normal ones because, as you saw, we have cheap apples and we have very expensive apples. And when we pay a high price for it, we want apples that are very nice. So if we pay 580 yen for one apple, we want it to be very good. Yeah. So today, basically, I'm going to talk about this part. So that was the introduction. Today, I'm going to talk about basically 4 parts. What is monitoring? The difference between 1-point measurement, multiple point measurement. Then I'm going to talk about the basics of measurement with light, because that's what I normally use for research. Basic things like wavelength, wave number, energy. I've talked about this in other classes, so maybe you remember them. Things like reflection, transmittance, scattering, fluorescence, and a very important law in the measurement of light, which is called the Lambert-Beer law. This is very important, a little bit heavy, so this will take a little bit of time. And then 3, I want to talk about how colors are expressed, because color is a very important aspect of measurement. And then finally, I'm going to talk about actual examples of how light is used in food monitoring, using visual light, near infrared, and fluorescence. Okay, so let's get in. What is monitoring? Monitoring is real-time observation and measurement. And even today, a lot of the monitoring work is done with the human eye. So we have people in factories, they look at products and they select the good ones, they throw out the bad ones. So you can imagine that this kind of work is very tedious, very, you get very tired, it's long time work. So we try to introduce mechanization where you can avoid this kind of long hour work. You can enable objective and stable evaluation. And you can also detect things that are difficult to detect with the human eye, like metals inside. And you can also measure things that cannot be measured with the human eye, like sugar content. Okay. So, what is ちょっとごめんね。はい、もしもし。はい。はい。すいません。私の部屋にかけといてくださいって言ってもらえる？ちょっと授業なんです、今日。すいません。はい。ごめんなさい。忘れてます。あ、はい。お願いします。ちょっと開いてる。ドア開いてるので入れちゃって大丈夫です。すいません。はい。はい。はい。お願いします。はい。Okay. Sorry. So, what is monitoring? There are 2 types of monitoring. One is called one-point measurement, where you measure 1 point per sample. So, which means that using that value is used to describe the average quality of that sample. For example, this is a place where they're measuring the sugar content of melons. So how much sugar there is in this melon. In this case, they have a belt conveyor. There is light that is shown onto the sample, onto the melon, and there is a detector at the bottom. And the light kind of goes through the sample, diffuses through the sample, and a part of it is detected in this detector. So actually, inside the melon, there are very high sugar parts and not very high sugar parts, right? So there's a difference within the melon, but this measures just one measurement. Multiple point measurement. So 1 point measurement, multiple point measurement. Multiple point measurement is also called imaging. It uses instruments with multiple sensors like a camera, and it measures the distribution or the position of components. For example, you can see an apple here. It's not measuring the average value, but it's actually looking at it as an image. And you see that there is more data than 1 point measurement. And, so you can really detect where it is bad. But of course, this can be more expensive than 1 point measurement. And if you think about imaging, and I explained that multiple point is using instruments with multiple sensors. You don't normally think of a camera as a multiple sensor equipment, but if you look at an image and if you make it really big, you have lots of pixels, and each pixel contains information. So that's what I mean by multiple sensors. A camera is a equipment that has thousands and thousands of sensors on it. And so, for example, when you say 4K resolution, it means approximately there are 4,000 pixels wide. So usually a TV with 4K is maybe like 3,840 times 2,160, 8 million pixels. So a lot of pixels, yeah. So 4K resolutions means really high resolution. There are a lot of sensors on this kind of equipment. Okay. So to wrap up, there are two types of monitoring methods: one-point measurement, multiple point measurement. Very simple. Okay, so let's go into the second part of this lecture, the basics of measurement with light. After this part is finished, we can take a small break, so please stay with me here. So light is a kind of wave, and I maybe taught this in other classes. It is a wave, so it has many characteristics. One important characteristic is the wavelength, which is the length from this point to the next point. So this corresponding point in a wave is called a wavelength. Wave number is 1 divided by wavelength, which is sometimes used. Frequency is how much it goes up and down within 1 second. And it is calculated by dividing the speed of light by wavelength. So you can see that longer wavelength, lower frequency. And energy is calculated by, it is correlated to the frequency. You multiply the frequency by h, which is a constant, Planck constant, and you get the energy. So the point here is short wavelength equals large equals large energy. This is very, very important. Short wavelength is equals large frequency equals large energy. Okay, and I'm going to show this here again. So with light, we have all kinds of different light. The light that you see is called the visual light. Is just a very, very small portion in the whole range of electromagnetic spectrum. So the visual light is between 0.4 micrometers and 0.7 micrometers of wavelength. This, you see the violet to the red, 400 nanometers to 700 nanometers. And if you go to this side, to the right, the wavelength becomes longer, frequency becomes lower, and energy is smaller. So infrared light, microwave light, radio waves, they have less influence on our bodies. If you go to the other side, you have shorter wavelength, you have higher frequencies, and larger energies. If you think of ultraviolet light, you know, that's very harmful for our skin. And if you think about X-rays, that's also very harmful. You have to take, you know, when you take an X-ray scan, you have to go into a room because it's very dangerous. And gamma rays are also very dangerous for our body. So you know that you can see that shorter wavelengths gives very kind of dangerous kind of light because they have such a large energy. So yeah, one of the things I want you to take back today is this basic relationship between wavelength, frequency, and energy. Okay. And so for light, there is this aspect of wavelength, but there's also different interaction between light and materials. Light interacts with materials in many ways. For example, when light enters a material, it gets reflected, it gets absorbed, it gets scattered, and also it gives out fluorescence. So reflectance, reflect, scattering, transmittance, and fluorescence. These are kind of 4 modes that light interacts with substances. And I'm going to talk about briefly about these 4 interactings. First of all, reflectance and transmittance. Reflectance is when the light kind of bounces off the surface. And transmittance is when the light goes through the material into your eyes. So the difference between this and this is the light is at the same side of the viewer, that is reflectance. So light goes from here to my eyes, that's reflectance. Transmittance is when the light is behind and comes to your eyes. And you can see this difference in these pictures. So when I ask you to imagine orange juice, I think you imagine a kind of yellowish, this kind of color, yellowish oranges, very nice. But when you measure orange juice with reflectance, like you put it in a paper cup so that there's no light coming from behind, the color you see is actually like this, kind of, I don't know the name in English, godoiro in Japanese, kind of brownish. So this is the difference between seeing the orange juice in reflectance mode and seeing the orange juice in transmittance plus reflectance mode. So you can see that our image of orange juice is made by the perception when we see the orange juice with transmittance, basically in a glass cup with light coming from behind. Basically, transmittance gives us a more light color. Okay, so that's transmittance and reflectance. Scattering. Scattering is a phenomenon when light goes through the material and then back. And it gives us this kind of white color. So this is a very typical phenomenon with light. This is an egg, and you know that the egg white is kind of yellow, a little bit, egg white. Yeah, the egg white is kind of yellowish and transparent, right? But when you mix it, you see this kind of white thing. Also with water, if you just see a bulk of water, it's transparent. But if you see snow, it's white. Yeah. So what's the difference between this transparent egg white and this mixed one? The only difference is that there is air inside. And when there's air inside, you have egg white, air, egg white, air, egg white, air. Yeah? So this kind of sandwich between different substances, it causes light scattering. And when light scattering occurs, we see a kind of white substance. Okay. This is also same with fog. Now, fog is just water, but it's in air. And because there is this water, air kind of thing, you see white. So this is scattering. And then finally, fluorescence. Now, fluorescence is a very kind of special light where the light you shine onto the sample is different from the light that comes out. So this is a fluorescence image of fungi, and the light that you're shining onto the sample is like UV light. So you don't see everything is black. Okay, but the mushroom, the fungi, looks green. So the light that is coming out of the fungi is green. Yeah? So different light. You can also see this with a shirt. If you have UV light, you shine it onto the white shirt, it looks blue. And blue light has a wavelength of around 450 nanometers versus UV light has a wavelength of around 350. So the light that goes into the sample is different from the light that comes out. So this is fluorescence. So we can use all these different kinds of interactions between light and materials in order to measure food. And I will talk about actual applications at the end of the lecture. Okay, any questions up to here? Okay. So the last part of this chapter 2 is the Lambert-Behr law, which is a little bit heavy. So please keep up. And if you have any questions, please ask. Okay. So Lambert-Behr law is a very, very important law when we talk about light absorption. This is the basic law that explains the relationship between concentration of a substance and the intensity of the light intensity, concentration and light intensity. And this is the basic equation that explains the Lambert-Behr law. If we denote the incoming light as I0, the light that goes in the sample, and the light that goes out, transmitting light as IT, we can define the absorbance as minus log 10 IT over I0. If we define the absorbance like this, we know that it is correlated to the concentration and the length of the light path. The length of the light path is how long this part is. So if we have the same tube, and if we change the concentration of something in the tube, then by measuring the incoming light and the outcoming light, we can kind of calculate the concentration of the thing inside here. Okay, so very important point is absorbance is defined by taking the log between incoming light and outcoming light, putting a minus on it, and the absorbance is linearly correlated to molecular concentration. Okay. So this is the Lambert law. I'm going to talk about why this occurs, especially why we need a log here. Yeah. So normally we don't like log. We want everything to be linear, but there is a reason why we need to put a log here, and I'm going to explain why like that. Okay. So this is the end part. I'm going to talk about each part very slowly. So let's say we have light coming in, and then it goes through this substance. And during a very small distance, while traveling through this material, some of the light is absorbed, and the light becomes half. Okay, let's say we have this kind of situation. What do you think happens if the light path is twice longer? So like this. How many of you think because in the first half it became half, it's gonna become 0? How many of you think because it became half first, it will become half again and will become a fourth? So how many of you think A? How many of you think B? Oh, okay. Really? Okay, yeah, that's correct. So when we have the light becoming a half of its original intensity in a certain length, then after the same length, it becomes half again. Yeah. So when light particles collide with liquid molecules, a portion of them becomes absorbed. So it's not become 0, it becomes half again. And so if we have 3 dx, it becomes half, half, and half. So let's say if we have 3 dx, at the end it becomes an 8. Okay? Yeah, you have the material with you. So, so let's think of another question. If the concentration is 2 times higher, it's more concentration. Okay. What would happen at the end? Oops, I put the answer. And so if the concentration is 2 times more, then it becomes a fourth again, a fourth again. So at the end, it's 1/64, while it's 1/8 here. Okay? So what we see here is when the concentration is 2 times, the light intensity at the end became not half, but 1/8. Yeah. So you can see that the relationship between input, ingoing light, and outgoing light is not like if you make it twice the concentration, it becomes a half. Yeah? It's like an 8. Okay, so let's try to find the relationship between all these kind of numbers. So I want you to calculate the amount of decreased intensity between the beginning of this part and the end, this part. Yeah. So beginning is I0, and at the end it's 1/2 I0. Yeah. So the difference is 1/2 I0. You don't have the material with you, right? Some of you have the material. You have the material in your, okay. So you have the answers maybe, but maybe you can try calculating. So please calculate the difference for here and for here. You want to take a little bit of time to, also in your head is okay. Try calculating the amount of decreased intensity. So the light intensity here minus the light intensity here. I can take a break. Okay, so that's not very difficult. For here, it will be half 1 I0 minus 4th I0, so 1/4. And then here, same, it's 1/8. So you can see that the amount of decrease is becoming smaller and smaller and smaller. And if we compare the initial amount going in with the amount decreased, initial amount going in and the amount of decreased, initial amount going in and the amount of decrease, you can see that there is a consistent relationship. It's always half, right? The going in is I0, it's half. If the going in is 1/2, it's a fourth. If the going in is 1/4, it's an eighth. So always half. So the rule here is that the amount of decreased intensity, I di, or minus di because it's a minus, this is proportional to the incoming intensity. And similarly, we can do a similar kind of calculation. The amount of decreased intensity is also proportional to the concentration and also to the path length. So if we put all of this together, the amount of decreased intensity minus di, this is proportional, or in Japanese it would be hide, also for Taiwanese people. It is proportional to concentration, incoming intensity, and path length. If we turn this into mathematical language, you know that when y is proportional to x, you say y equals ax, as a is the coefficient, right? So if decreased intensity minus di is proportional to concentration, incoming intensity, and path length, then we can put this all together and we can say minus di equals something di and dx. If I explain this a little bit, if decreased intensity minus di is proportional to concentration, then minus di equals AC. If decreased intensity is proportional to incoming intensity, minus di is BI. And then if decreased intensity minus di is proportional to path length, then we can also make another, yeah? And we can put them all together and say minus di is A, B, C, C, D, C, I, dx. And we can change this ABC to epsilon, or any kind of coefficient, okay? So we've arrived, by looking at this kind of diagram, we've arrived at this equation, minus di equals epsilon CL dx. So what do we do with this? Yeah, I put this here. Minus di equals epsilon CI dx. Yeah, what do we do with this? There is like a method that everyone uses in this kind of situation. You put all the same variables on the same side. That's like a normal standard way of calculating these things. So what you do is you bring, because there's a di here, you bring the I to this side. Yeah, and you have dx here. Yeah. So we see we have 1/I here, and then we have epsilon c and dx here. And then we can integrate both sides. Integrate for I to I0 to IT, and we can integrate x from 0 to L. And this will lead us to here. If you remember, if you integrate 1/x, you get log. Yeah, that's a little bit of mathematics that we have to remember. Okay, so that's the reason that you see a log in this equation. It's very important. So that was long. You don't have to remember how to calculate this. I'm not gonna give you in the evaluation something that you have to calculate. Go through this kind of mathematics. I just want you to remember that there is a log in this calculation of the absorbance. Yeah. Log 10. So what does this mean? It means that the absorbance is actually very important. Let's say when absorbance is 2, it means that 2 equals minus log 10 IT I0. And this is a log 10, right? So this means that the original light has become 100th when it transmits through this. Yeah. So when absorbance is 2, it means that the transmitted light, the light that goes out of the material, is 100th of the original light, so very weak. If absorbance is 3, it means that the transmittance is 1,000th of its incident light, very low, right? So when you do this kind of measurement, you need to be very careful. If you get an absorbance of over 2, it means that your sample is so highly concentrated that it's absorbing most of the light. And a machine is trying to measure the very, very weak light that comes out of the sample. And you can get wrong. You can get very high errors with this kind of situation. It's important that, for example, you adjust the concentration, you dilute it, so that the absorption is lower than 2, which means that the outcoming light, the transmitted light, is not that weak. We use a lot of this kind of absorbance test in our lab, and I always ask my students, what was the actual absorbance? Sometimes the absorbance is very high, maybe not 2, but like 1.8, 1.9. In that case, I get a little bit cautious, and maybe we should, dilute the sample more, because you can get very fluctuating results when the absorption is so high. Okay, so that's until the second part of this lecture. I think we can take a break here. I don't know, how many minutes does teachers take? 10 minutes? 15? 10? Okay, let's take 10 minutes. Come back at 15 past, maybe 15 past. Yeah, 15 past a little bit more. Yeah, 4時15分、16分ぐらいで。
I cannot just walk on that side and that professor is not even present. So it's technically these professors, this one, both of them are in the same lab. This one is the photography who is working with the model of the combining their pictures. Advisor, academic advisor is this one. You have to write online right now. Yeah, you get clean shave, but I mean, it is. Do you use safety razor? No, the one without safety. I mean, it's the blade. No way. I want to get a safety razor to save money on the blade. But I don't know if I'm gonna get now. What do you mean safety razor? Someone with a removable blade, individual. As opposed to the blade where you get the big stuff too. Cheaper than. It's not that much. Otherwise, we can do Gillette. Barbers and this was random. Yeah. My barber was no, Mandarin. I know, right? But those places are really cleaner than. Very fun. I didn't buy it. Just say you're learning to, I might be, I'm not, I don't know.
I feel like I am.
I have cereal every morning, pretty much. Really? Yeah.
I don't know what you make. Because you said you were so hurt.
You can't have cereal. Maybe like you have less
I heard that people develop it. When you're
When it's warm, I don't know, maybe it's curdle the milk or something. Yeah, Peter, or. No, we don't have the fat.
Okay.
I don't know.
Okay. Now I think we can start the latter half of the class. Yeah, I always kind of don't take that long for my class, so maybe we'll end early today. Colors. But a very important aspect of all kinds of sensors, including the human eye, is that sensors can only detect intensity, which means dark or light. That's basic rule of all kinds of sensors. Light, a lot of light or less light. And the reason why we can see the world in colors is because we have three sensors in our eyes. We have a sensor that is sensitive to the blue light. We have another sensor that is sensitive to green light, and another sensor that is sensitive to red light. So it's very remarkable that each of the sensors only carry information about how light it is or how dark it is, but by combining information from the three kinds of sensors, our brain automatically converts that kind of information into colors. Even when I know this kind of information, it's very strange that, with no time at all, my brain is able to combine the three sensors and then see everything in colors. So in a cross-section image of our human eyes, you see these kinds of rods and cones at the bottom, and there's a lot of them, but each of them are either blue or green or red sensitive. So what our eye is actually seeing is we're seeing three images. The red cone is seeing an image like this. The green cone is seeing an image like this. And the blue cone is seeing an image like this. And our brain puts that together and we see this kind of color. And the red color means that there is a lot of signal in the red, but low signal in the green and blue. For example, if you look at the tomato part, you see that it's very white here, but dark here, right? This combination of light, dark gives us the perception of red. If you look at this green part, the red is much darker, the green is a little bit lighter, and the blue is very light, very dark. So this combination of a higher green, a little bit of red, very low blue gives us this kind of greenish color. And you can see if you look at the white part, this is a part where all of the cones see high intensity, right? So high intensity for the red cone, high intensity for the green cone, high intensity for the blue cone gives us a white color. And conversely, a low intensity for the red, low for the green, and low for the blue, it gives us a very dark, like almost black color. So this is how humans see, and this is also how a camera sees. So in a camera, there is also sensor. In a color camera, like your phone, there is a sensor for the red, sensor for the green, sensor for the blue, and the combination of these three sensors gives us a color image. So if you look at, well, actually that is how I came up with these colors in my PC. I took this image, I read it onto my PC, I divide it into these three RGB layers. There's a specific software that you can do this, and I just showed them in grayscale. So basically red, which is light at 700 nanometers, green, which is light at 546 nanometers, and blue, which is light at 435 nanometers. These are combined to express colors. And if you have 001 RGB, red, 0, 0, 0, that gives you black. And if you have a 1, 1, 1, it gives you white. Yeah, so this seems good. So actually, if you look in here, if you look through a microscope at this TV, this white part is going to show red and green and blue at the same time, and that's why it looks white to you. But this is kind of counterintuitive. You know, we are used to mixing paints. We are used to mixing paints. If we mix red and blue and green together with paint, you get black, right? So you don't get a white when you mix R and G and blue, blue. So I'm gonna show you a video which I showed in also other lectures, so you might already know that you can also actually get white when you mix red and blue and green light. And the video is in Japanese, so if you're tired with English, then it will be good for you. Sure. Yeah. Yeah, it's already started. Yeah. I hope this goes into the video then recording, but.
暗闇の中にぼんやりと見えるこの物質は、イムスが開発したサイアロン蛍光体。紫外線を当てると発光し出す。
So this is called the silent
こ
phosphor
のサイアロン
and
が LED 電球や
it
液晶テレ
shows
ビを
white light, as
実
you
用へと
can
結
see.
びつけた。しかし混乱させるようだが、実はこのように白く発光するサイアロンというのは存在しない。
So
物質は何なのだろう。
and
この映像を冒頭の部分から逆再生すると、それが明らかになる。
so they're gonna show the video backwards. So you can see that the person
核
is
反応で
mixing.
粉がかき混ぜられている。緑色の物質が見えてきた。
You can see it was
緑色に
originally
光る
a mixture
ベータ
of
サイアロンだ。
green. And
これ
you
を
can
取
take
り
it
除
away.
く。
So remember, it's
つ
videos
まり
backwards.
この時点で緑色の物質が加えられていたということになる。さらに逆再生を続ける。今度は2つの物質に分かれた。青色の物質を取り除く。すると赤く光る物質が残る。
So you can see that originally it was
赤、
blue
青、緑。
powder,
つまり
red powder,
光の
and,
三原色に光るサイアロンを混ぜ合わせることで、
and you
先
get
ほ
the
どの
white
白
powder.
く光る物質が構成されていたのだ。そして液晶テレビや LED 電球の実用化は、このさまざまな色に光るサイアロンができたことで達成された。
Okay.
未来の科学者たちへ。ニムス。
So, yeah, I think that this kind of silent phosphor is used in maybe this TV as well. And that's how you see the white color on this TV. This is also a mixture, very fine mixture of that red one and the blue one and the green one. So even though it's hard to believe, that is actually what is happening. And the data that you see in computers, digital cameras, TVs, they are all made up of 3 layers, maybe sometimes 4, of the red image, the green image, and the blue image. So if you have specific software that can do this, you can take any image, read it in the software, and you see the 3 layers of the red image, blue image, and the green image. They are all constituted of just numbers. So if you just read this, it will become a black-white image. But when you combine these 3, you get a color image. So this is the RGB color coordination system. You have the R, you have the G, you have the B. So if you put a certain value in each layer, you get a certain color. But this RGB color coordination system is not the only color coordination system that we have. We have others as well. And another color coordination system that is used a lot in measuring food is called the L star, A star, B star color coordinate system. So please note that in all kinds of color coordinate system, you need 3 or more axes to express colors. And the L star, A star, B star shows the colors in L star, which is light or dark. A star is green to red, and B star is blue to yellow. So this doesn't show the L star color coordination, but just the A and the B. If you go to small minus A, you get green, plus A, you get red, plus B, you get yellow, plus minus B, you get blue. And so if you have a certain combination of A and B, you can get a certain color. And the good thing about this A star and B star and L star color coordination, this is close to the human perception, which means that very different colors give us the perception of a different color in our eyes. This is not true for RGB. For example, for humans, we are not very good at separating these two. Humans are not very good at distinguishing between this kind of blue-green region. So I think for you, these two colors look very different, but these two colors look a little bit similar. Yeah, even though they are in this RGB space, they are equally spaced. Some of these colors look a little bit similar. Some of them look very different. So that's the problem with the RGB. But with L star, A star, B star, different values look different for us. Similar values look similar to us wherever you go. So close to the human perception is the reason why we use the L star, A star, B star color coordination system to measure food. So it's used to evaluate color of food or industrial products like paint. For example, if you're making cars and you make, I don't know, Forester something. I go on a Forester, so. And you buy a red one. Then you want the red to be a certain color, right? I think the Mazda cars, Subaru cars, and Toyota cars, you can have red cars, but they are slightly different. But if you want to buy a Subaru red car, it should always be the same red color, right? So the paint has to be exactly the same red. And the way you evaluate it is you evaluate it with the L star, A star, B star color coordinate system. You give it a certain value, and then it will always be the same red paint. So that's how it's used. Example of this is when we measured the color of red during baking. So this is the actual color. It started off as kind of whitish. So the bread dough is white. And when you put it in the oven, it becomes darker, but it also becomes kind of redder. So the A star, B star, and L star values change. And I think this was a video. You're sure. So you can plot these colors in the A star, B star, C star, L star color coordination system, and you can see how the colors changed through the baking process. So basically, as the baking proceeds, the L star goes down. Yeah, but it's not only the darkness changes. You can also see from the beginning, if you look at this from the top, you can see that it's also a kind of round shape, right? So as the baking proceeds, the color changes from this kind of A star, B star to it's kind of going round into here. So this is how we use this kind of color coordination system in research. So the final part of today's lecture, examples of food monitoring. So how do we use the information that I just gave you to monitor food in real life? So the first range of light that we can use is the visual light. This is the light that we see with our human eye. Again, it's between 400 and 700 nanometers. Because we see it, there's a lot of cheap light sources and sensors, very high quality. Your phone is a very good one. And because the sensors are cheap, you can do multiple point measurement and also line sensors like images. So let's see an example. Let me do this. So this is a date sorting machine. And you can see this is a camera here, right? And very fast. And this is shown very fast image processing. And the bad ones are moved to the second lane very fast. So that's how you would measure the length, the width, and the quality. So that's for people who want to buy this. Okay, so the point here is if you use visual light, there are a lot of cameras, there's a lot of light sources which are very cheap, very fast. And if you combine it with image analysis methods, yeah, that's like the state of the technology right now. Very fast and very accurate. Okay. So let's move on to another kind of light, which is called near infrared or NIR. First, infrared is the light between 800 nanometers to around 1000 micrometers. That's the infrared. And the near infrared is the infrared light that is the visual. And it's basically from 700 nanometers to 2,500 nanometers. That is called the near infrared region. Characteristic of infrared light is that it can measure the vibrational energy of molecules. Vibrational is, that molecules are vibrating, and the energy of vibration is specific to the kind of molecular bond that they have. So if you have an OH bond, if you have a CH bond, if you have an NH bond, they all vibrate at a certain energy. So if you can shine a light of that same energy onto your molecule, it's gonna absorb light. So that means if you have a broad range of light and you just shine it onto your sample, it will absorb the kind of energies that are related to the vibration of that specific molecule. So that means you can measure OH bands, CH bands, and NH bands, etc. All kinds of molecular bands. So infrared is connected to vibrational energy. By the way, ultraviolet, visual, this kind of range is connected to electron energy. So the transmittance from electron to one state to another state. So that's a larger energy. And each of these regions are related to different kinds of energies. So the use of infrared light to measure molecular structure is very is used a lot. But you can also use microwave to analyze maybe things like water or larger structures like third structure, that kind of thing as well. So different wavelengths are correlated to different structures, and infrared is related to vibrational energies. And near infrared is a very special kind of light, and its characteristics are it has weak absorption, and its spectra is complicated, and it can only measure organic substances. So weak absorption sounds like it's bad. If it only absorbs a little bit, then it seems, not so nice. But it means that the light travels far inside the sample. So it's possible to measure constituents inside your food. Like if you have a melon, our visual light only travels to the outside. Yeah, we can only see the outside of the melon. We cannot see the inside. But if your eyes were very special and they were able to see the NIR light, everything basically would look transparent to us. NIR light travels inside things. It has low absorption, which means it has high transmittance. So absorption is a very good thing when you want to measure food, because normally we are very interested in the inside of the food, where we can see the outside. What we want to know is we want to know the inside of the food. We want to know the inside of the watermelon. We want to see inside of wheat kernels. We can see the outside, but we want to know the inside. So weak absorption is a very strong advantage when we want to measure. But there are disadvantages with NIR light. The biggest disadvantage is that the spectrum that we obtain from mixed materials is very complicated. So you cannot take just one wavelength and say that the absorption was very high, so there must be lots of protein. That's not possible with complicated spectra. you need a lot of multivariate analysis and special methods called chemometric methods to obtain this kind of quantitative information. And that is why the development of NIR light was very late compared to IR, infrared, or other regions of light. It was only in the late 20th century, like 1980s, 1970s, 1980s, that NIR light was actually used for agricultural products. Because we need a lot of complicated methods to analyze the data. And nowadays we have computers, but yeah, we can only use that kind of sophisticated machines to do that. And another important point is that you cannot measure inorganic components. Although, for example, with salt, it affects the vibration of water. So you can measure salt content indirectly by looking at the vibration of the water molecule. So not directly, but sometimes indirectly. So what do I mean when I say that the NIR spectrum is complicated? This is an absorption spectrum of cookie dough. And you know that in cookie dough, we have water, we have fat, and we have protein, and we have carbohydrates. So kind of complicated. And when you measure a cookie dough, you get this kind of spectrum. First of all, I think you notice that it's kind of going up. When the x-axis is the wavelength, if with longer wavelength, you have higher absorbance. That's the basic trend. And then you have these kind of squiggles. And with the same, you have several peaks, like you have one here and you have one here. Also with water, you have one here and you have one here. And then this is a OH band apart from water. And you can see that they're kind of merged. So you cannot just take this peak and say we have a lot of water or we have less water, because the peaks are all kind of mixed. So what we do, we normally take multiple peaks and we try to make a kind of model to estimate the compound that we are interested in. For example, this is a standard curve to measure the amount of protein in wheat. And you can see that it's looking at the reflectance at, sorry, it's very small, 2,180, 2,100, and 1,680. It's taking the log, and then it's multiplying it by a certain number and adding it up. So this kind of selection of the wavelength and multiplying them with a certain value and adding them up or subtracting, this kind of calculation is needed in order to estimate the amount of protein. You cannot just look at one wavelength. And this is actually a very simple model. You just have 3 wavelengths and you're just multiplying and then adding them up. But normally when you do measurement with NIR, you basically look at the whole spectrum and you have to come up with different multivariate analysis to estimate. So you use methods like machine learning in order to get a good model for this. This is another example where NIR is used to measure the sugar content of foods. I think you saw an image of a melon being measured. This is similar. You have an orange you have light at either sides of the orange, and then you have a detector at the bottom. And what we do is we normally try to calculate the value with this light sensor, and then we try to correlate it with something that we know is measuring the sugar content, something like Brix, which is a kind of measurement of sugar content. So this making the model is actually quite hard. But this is also already used in industry. I think this is,
久保田が開発したフルーツセレクター搭載
this
型
is
選果
called
機
a fruit
選果工
selector,
房は糖度、酸度、重量を同時に測定することができ
and
ま
it
す。
measures the sugar and the
大
acidity
型の選果場で使われ
and
る
weight
糖度
of
計っていうのは
tomatoes.
1台が1000万以上とか、まあ非常に高額なものでして、こちらはまあ糖度計の方は1台100万円ぐらいということで、まあ、
So
担い
1
手の方
million yen.
というか中規模農家さんにもお使いいただけるような価格に設定しております。こちらは光センサーを用いまし
So you can see
て、
that there was light
トマトの
coming in.
中を光を通しまして、その返ってきた光を分析しまして糖度を測定しております。はい
So in this system, the light comes from
フ
the
ルーツセレクターを
biddies
2台搭載したユニッ
the
トに
sensor is also
1人で
biddies.
トマトを測定した場合、1時間に約2000個を処理することができます。
この配下するとこを増設したり、このフルーツセレクター計測部の台数を変えたり、でタッチパネルをパソコンに変えたりという、そういう拡張性はあります。今は糖度と酸度を測っているだけなんですが、まあ、今後はまあ腐った果実を測ったりですね、他の障害度を測ったりとか、そういうふうにしてまあ選別できるような展開を考えていきたいなとは思っております。
糖度と酸度を測る品目としては、トマトとリンゴ。糖度を測る品目としては、梨、柿、キウイ、ビワなどがあります。パソコン仕様の標準タイプは、フルーツセレクター1台、配下工数7つで構成され、販売価格は約510万円です。
5 million yen for basic combination of the sensor and everything. So Kubota is the company who made that machine, and they have very sophisticated. Also, they have like a handheld system that you can take into the field, and you can measure fruits on the tree directly. So, yeah, what they're saying is, you know, before harvest, you can check your fruits, and if they are ripe, then you can harvest them. Yeah, so that sounds very nice, but you know, things like tomatoes, fruits, maybe not apples, but things like pears, you harvest them in the summer, yeah, and it's really hot, and you don't want to take a sensor around you and then measure them on the tree. So I think my personal opinion is that we can't just have a sensor. We need something like a robot to help us measure these fruits. I think in Tea Park, they have that kind of mobile sensor. So if you're interested, you can help measure them on the trees in the summertime. I don't know how. But yeah, so this kind of technology is already quite well made, and you can measure things like sugar content, acidity, and also things like if the inside is rotten, that can also measure that. So that's NIR. Oops. Another example is fluorescence. So fluorescence, as I explained earlier, it's a kind of very special light where the light that is shone onto the sample is different from the light that comes out. And only very specific chemicals have this kind of fluorescence characteristic. Some things like proteins, also polyphenols, what else? Chlorophylls, very specific constituents. And this means that fluorescence has very high sensitivity to some constituents because you know, your food is a mixture of all kinds of constituents. I think there's like thousands. And if your light is sensitive to all of them, it means you have this kind of mixed spectrum and it's very hard to understand it. But if your sensor is only sensitive to specific constituents, it means that you can measure them in a very high accuracy, right? So fluorescence has very high sensitivity for some constituents like proteins or color pigments or polyphenols. But on the other hand, on the flip side, you cannot measure constituents that don't have any fluorescence like carbohydrates and normal simple fatty acids. So there are things you can measure, that's very good, but there are things that you cannot measure. And this is an image of rice. So rice has an outer layer that contains some things that emit fluorescence, and it's very hard to see from these images actually. But as the storage time increases, the substance that gives out fluorescence also increases. So fluorescence monitoring enables us to see how bad the rice is by looking at fluorescence. So basically, when the fat is oxidized, it begins to emit more fluorescence. So at the beginning of storage, it looks a little bit dark, but after 7 months, it's much lighter. Or you cannot really see it very much on this screen. Anyway. Okay, so these have been examples of food monitoring. Any questions until this part? Okay. So now it's almost 5 o'clock. Okay. So a quick summary of what we learned today. What is monitoring? What is monitoring? Point is there is 1 point measurement and multiple point measurement. Okay, that's the most important point. Okay, so let's look at the examples that I've showed you. For example, looking at protein and wheat, you see that there's 1 point for one sample. So this is a 1 point measurement kind of example. Also for this is taking 1 point from an orange, 1 point measurement. But on the also the tomato. But if you think about the date example, this is a multiple point measurement. So for one date, you are taking an image, and from that image, you are able to find out the blister analysis, the loose skin part. Okay? So 1 point measurement, multiple point measurement. Okay, a recap of the second part, the basics of measurement with light. I talked about the Lambert-Beer law, and to recap, it is defined as taking the log between the incoming light and the transmitted light, and that the law says that the log of this is linearly correlated to the concentration. And as I explained, because we're taking a log, you need to be very careful of the absorbance value. If the absorbance value is over 2, it means that the transmitted light is 1/100th of the incident light. So you should always adjust the concentration that the absorbance is not so large. Okay, so that's the most important part about the second part. Third part, how colors are expressed. So I talked about the RGB color system and the L star, A star, B star color system. There are more kinds of color systems, but the important thing is you need multiple channels to express colors. For the RGB, it's the red channel, green channel, blue channel. For the L star, A star, B star is the L star, lightness channel, A star, and B star, which defines the color. And for examples of food monitoring with light, I explained some examples which are already used in the industry, like visual light, near infrared light, and fluorescence. And taking the last part of the lecture, sorry, I end very early. I just want to explain a little bit of a technology that I have been developing in my lab, which is called fluorescence fingerprint, and which is like advanced version of this fluorescence. So I explained that fluorescence is given out when the light that is shone onto the sample is different from the light that comes out. And the light that we shine onto the sample is called excitation light, and the light that goes out is called the emitted fluorescence. And normally in normal kind of fluorescence measurement, you choose a certain excitation light. For example, I've chosen here to use with a red light, and you take one emitted fluorescence spectrum. But this doesn't work very well in a kind of food system where you have lots of components that are mixed. You don't know which component is going to give out fluorescence. So the fluorescence spectrum, the fluorescent fingerprint is a way where you use all kinds of different excitation lights, and you measure the emitted fluorescence for each kind of excitation light. So in the end of the measurement, you have excitation light wavelength, emission light wavelength, and the light intensity. So you have this kind of three-dimensional data set. And if you look at this from the top, it looks like this. So you have excitation, emission, axis, and the intensity, the strength of the light, is shown in the color. Yeah. So the reason why we call this the fluorescence fingerprint is because this looks like a fingerprint, and it shows the different all kinds of different chemicals in this sample. The characteristics are that even if the main components in your food are the same, if you have a slight difference in fluorescence characteristics, you can detect them with this fluorescent fingerprint, and you just shine light on it, so it's a non-destructive observation method. So this is a kind of experiment that we did before, quite a while before. So we measured mangoes, and we tried to find out where they came from. The reason why we did this experiment was that in Japan, we have mangoes that are imported from Taiwan, but we also have mangoes that are made in Japan from Okinawa and in Miyazaki as well. And we tasted all these mangoes. Basically, they don't differ very much, but you know, Japanese people like made in Japan things. So basically, Taiwanese mangoes are very cheap. Okinawa mangoes are a little bit expensive, maybe like 400 yen for Taiwan, Okinawa 1,000 yen, and then Miyazaki is like a brand, so 3,000 yen to 4,000 yen per mango. Wow. So this was such a nice experiment. We get to buy all these mangoes, very expensive, and then we measure them, and this is a non-destructive measurement, so we get to eat them afterwards. So yeah, that was the real motivation actually. But yeah, there was this problem where a Taiwanese mango was labeled as an Okinawa mango, and that's how they tried to get more money. So our real motivation was somewhere else maybe, but the motivation behind this research was that we want to have a technology that can determine where the mango was made actually. So we brought all these mangoes from a source that we know is true, and then we measure the fluorescence fingerprint of all these mangoes, and then we try to do some multivariate analysis. And basically, it was possible to separate Taiwanese from Japan, and Okinawa and Taiwan and Miyazaki as well. So this was, measuring the fluorescence fingerprint takes like a few minutes. So with a few minutes measurement, it was possible to separate between different geographical origins. So you can do this by just measuring the skin. So it's very quick and easy for determination. And we showed that also this same method can be used for other things like potatoes as well. So the reason we were able to separate is not very clear. Right now, we didn't quite go into the mechanism of how we can separate between different countries and different origins. But we have a hypothesis that when Taiwanese mangoes come into Japan, they are basically heat treated for a very short time because there are bugs inside the mangoes, which cannot be transferred from other countries into Japan. So a lot of the agriculture products that are imported, they need to be quickly heat treated in order to kill those bugs. So we think that heat treatment changed the skin characteristics. And also between Okinawa and Miyazaki. So Miyazaki is a little bit higher up than, a little bit to the north than Okinawa. So in Okinawa versus in Miyazaki, they are grown in warm, houses. Yeah, what you call them? The plastic houses. House. We call them in Japanese house. The plastic thing that you grow agricultural products in. What's the English word?
Greenhouse.
Greenhouse, greenhouse, So in Miyazaki, the mangoes are grown in greenhouses. In Okinawa, they're grown outside. So maybe that affected the skin, and that's maybe why we were able to differentiate between different places. So that's our hypothesis, but we don't actually know. Okay, so this is one example of using the fluorescence fingerprints to differentiate between samples from different areas. You take 2 to 4 types of natural cheeses that are made from milk, from cow milk, and then you mix them. You heat them first, and then you cool them down to get your cheese. So that's like, when you have the sliced cheese, the thin one that you find in Japan. Also, what else? What kind of cheeses are there? The small ones that you eat while drinking, that kind of cheese is processed cheese. And the good thing with processed cheese is because you mix different cheeses together, you can get a very consistent quality. So every time you buy, I don't know, a Morinaga sliced cheese, it tastes exactly the same every time. And you don't see that with natural cheese because natural cheese changes with the season, etc. So the company normally uses natural cheese, which is imported, and they mix together 2 to 4 kinds of cheese to get the same desired quality. And because this original cheese is imported, they don't know actually if it's very fresh, not mature, or more mature, like old. And to get a consistent quality, they need to mix a fresh cheese, which has a lot of structure with a mature cheese, which has a lot of taste. So it's very important for them to know what their ingredient is like. Like, is it fresh? Is it old? And currently, they have experienced professionals who touch and taste the ingredient that they use every day, and they kind of decide, okay, today we're gonna mix 30% of this, 40% of this, and then 30% of this. So they are professionals and they know what they're doing. So that's why we get very consistent quality. But the motivation from this cheese company was that they wanted to have more different ways of measuring how mature or how fresh the cheese was. So what we did was we also got lots of different cheese of different maturity, so matured for different periods, and we measured the fluorescence fingerprint. We tried to predict how mature the cheese was. And so here you have a graph showing the actual maturation period. So in this case, we use cheese that we know how old it was. And then this is the predicted maturation period. And you can see that basically it's kind of goes on the same line, which means you can predict or estimate the maturation period from the fluorescence fingerprint. This is the actual maturation days, and this is the maturation degree, which is calculated by the amount of soluble nitrogen over total nitrogen. So as the cheese matures, you get more soluble nitrogen, and so that's the maturation degree. So basically, this shows that maturation can be determined quite easily by this kind of non-destructive measurement. And then finally, this experiment we're doing right now as well, we try to estimate the ripeness of avocados. So you know that avocados are green like this sometimes, and then red, black, brown sometimes like this. Avocados are very special fruits. When you leave them on the tree, they will just be green, even if you leave them for like 3 months, I think. And then when you harvest them, once you harvest them, they begin to get brown and soft. And depending on the timing of your harvest and depending on the temperature that you leave the avocados after harvest, the speed at which it ripens is different. And yeah, the color tells us whether the avocado is ripe or not. But I think you've had experience where you think that it's kind of ripe, but you cut it and then it's very hard, or you look at this and it looks very nice, but when you cut it, it's like too soft. So we tried to determine if the avocado is ripe or not by measuring the skin and the flesh. So this is just a preliminary result, but we saw that when we measured unripe and ripe and overripe avocados, there was a difference in the fluorescence, especially a fluorescence here of chlorophyll A, and we saw that the chlorophyll decreases as the ripening progresses. So basically, by measuring the fluorescence fingerprint, we can determine when's the best timing to eat the fruit. So this was also like kind of a motivation from everyday experience where we want to know when to eat the avocado. Okay, so these are some examples in the lab, which are not actually, in the industry right now, but some of the research that we do. Okay, so any questions? You can ask questions through the Slido form at the beginning. You can ask them here if you want. Any questions? Yeah, it's kind of hard to ask questions. Oh yeah.
Yeah. So what exactly do you see the differences between the avocado under the fluorescent fingerprint and just by visual examination?
Okay, with visual, the difference between fluorescence fingerprint measurement and visual inspection, you mean?
Yeah. Are there any, besides the chlorophyll color changing, because that's usually a green color.
Yeah, it's true.
If an avocado becomes, if it ripens and it turns black, would there be anything noticeably different over one that is black and that might still be unripe?
Yeah, that's a very good question. So, yeah, it is true that chlorophylls are green. Basically, they look green to our eyes. So as the chlorophylls decrease, the color basically changes from green to blackish. But the color that we see is not just the influence of chlorophyll. It's the combination of chlorophylls and as well as other kinds of color pigments in the avocado, like anthocyanins, etc. And the color that we see with the eyes is the combination.
Right.
While in the fluorescence fingerprint, you can kind of separate them by changing the wavelength that you measure.
I see.
So right now, we are measuring different excitation wavelengths versus different emission wavelengths. And you can see that there's a thing here that doesn't seem to be changing, and there's a thing that seems to be changing.
Yeah.
But in other, so these are just 3 examples that I've been showing you, but there are other samples which have different intensities here, which would give us a different color, but we can look just at the chlorophyll, and that gives us a more accurate estimation of the ripeness.
Okay.
If that's
Thank you.
a good answer. Thanks. That's a very good question. Other questions?
Oh, sorry.
Yeah.
I was actually a little bit confused about the geographical origin.
Okay. Yeah.
The graph. I'm wondering what the axis means.
Yeah. Sorry for not explaining that. So yeah, this is actually I just show this one axis, but this was calculated by adding or subtracting the value at certain fluorescence combinations. And the combination, I forgot the specific combination, but I think it was like 5 or 6 wavelengths. And the way we come up with these specific 5 or 6 wavelengths is by doing a kind of calculation where we randomly take some kind of wavelength. We see if that separates between different countries or different geographical origins. If it works, we take it. If it doesn't work, we throw it away. So you cannot do that manually. So we do that with the computer data analyzing software, where it will automatically kind of choose the wavelengths that correlate best with this kind of difference.
So these clusters actually show their similarities, but within this cluster points, they are more similar. So that's why we can separate these three.
Yeah. Exactly. So with this kind of axis, the Japan origin mangoes have similarities in those wavelengths, whereas the Taiwanese ones have similarities in same wavelengths. Yeah.
Thank you.
Others? Yep.
The maturation of G slide, you talked about the soluble nitrogen.
Yep.
And what is the other indicator that you talked about?
Here is the so the maturation degree is calculated by the soluble nitrogen over total nitrogen. Yeah. So when you change the total nitrogen is kind of equal to protein content, that may differ a little bit from cheese to cheese, but once you make the cheese, it's the same. And as the cheese matures, the part of the when you have the total nitrogen, a part of it becomes soluble, and the ratio becomes larger as the maturation progresses. So basically, the molecules become smaller and smaller, but the total nitrogen is the same. Good. Nice that we have questions. Okay. So I always end like this, and I get tired of talking. So I ask you to do something at the end. So I'm gonna ask you this: do you still have the form that was shown to you at the end of the presentation? At the end of the first questionnaire. If you don't, I'll try to get the QR code. But the final question is that I want you to imagine that you are the manager of a supermarket and you want to maximize your profit from selling apples. And what will your strategy be like? What kind of technologies will you use? How will the price of your apples be, and what kind of people will you be targeting? So I'm not going to evaluate you on this. I just want lots of opinions. And it would be nice if you can use the technologies that I introduced today. But of course, you can be like, I'll just make it cheap and that will be the end. No technology. That's also okay. But please write like what kind of people you will be targeting. Okay. And we will look at maybe you can take like 10 minutes to write that down, and we'll look at some of the answers at the end. So maybe I should show the URL. So what will this give us? Okay. So those of you who don't know the URL for the final question, I'm gonna try to make it. It's best if I do this. Just download. And then put it on the slide. Okay, so this is, if you haven't got the, if you don't have the QR code, this is it. You can take it. And maybe I can start reading the answers around 35 minutes past 5. I can just
Lu coba apa? Lu coba apa? Coba kamera. Coba gua pakai semua. Tapi yang murah-murahnya. Oh.
stop sharing. And take off this for a moment. Yeah, if you can write it in English, that would be appreciated. But Japanese is also fine.
Kamu mau ngeliat apa? Lu udah. Lu cuma pakai one point measurement aja. Terus jadi murah banget ya.
Please.
Kayaknya kayak kesel kan tadi. Oh, awal dia berpan. Menjadi sushi bang. Kok kayak begini? Gua stagnya berjadi. Kalau gimana? Tapi nggak tahu sih. Jadi lu solusinya Pokemon gitu. Karena Pokemon gue nggak gue bahas. Soalnya gue baca lagi. Compare to sports, soalnya gue bilang ke dia. Yaudah. Apa? Gue bilang ke profesornya compare to sport. Jadi lu maksudnya menurut mereka main sport gitu? Enggak, gue bandingin semua sport. Bandingin? Kayak gini. Gue yang ini kan itu gue ngajarin. Langsung beli langsung gue. Ya lain spesifik gue. Oh gak ada nama ya? Oh no. Senang gue.
No, this is last year. This is from this year. Well,
Soalnya itunya jelek banget gue, tapi packingnya bagus banget gue. Terus lu bilang gue iya, oke. Gue juga bilang gue tahu. Saya gue nggak ngerti nanti tahu ya gue. Tapi gue nggak ngeliat mana yang di sini.
what? It's not really showing.
Tunjukin nama please.
Yep.
Wah takut banget. Ini jangan tunjukin nama sih. Enggak. Cuman yang bawah itu
Very fun. Very interesting. What? Oh my God. Boy, no.
Kan yang nggak tahu yang mana.
More than 100% off.
I can use labor from high population countries. I don't think it's a Japanese person. I mean, if we wrote that, we would be very. I don't think it would be. Yeah, I'm not looking at the person.
Oh my god.
Of course.
Sorry, I need to share it with the students. Sorry. Yes. I'm sorry for students. Taiwan. I think I've shared the screen. Okay, sorry. Me too. So thank you very much for all your very nice comments. So yeah, there's no correct answer. There were some that actually will measure their sample, their apples, measure their quality, and then try to change the price based on quality. There were very nice, very nice positions, like polish them, use cheap labor, use advertising, also there was like cutting rent, right? Yeah. So, I don't know. I'm not a supermarket manager, but I do think that, places where they give you some food to eat, there's a lot to think about there, right? You want to give the people some nice things to eat, but maybe that's like cut fruits. But you also don't want to waste the good stuff as well. So cutting fruits, processing them. So I think also nowadays in supermarkets, you see supermarkets who have a lot of processed things like obento and, ready-made things. So I think probably the low quality agriculture products can be used for that kind of purpose and get high profit there. A lot of strategies which are very important, very nice, I think. So if you go to the top, the first one here today was high quality. I would category sort apple varieties. Higher quality apples would be priced more expensive than low quality apples. Depending on the scale of the supermarket chain, I might use inspection by hand or crate rather than use high technology sensors. Of course, that's a good choice. Sugar content can be determined through NIR sensors because we cannot really see them. Apples will be located near the front of the store alongside other types of produce. Higher quality apples will be closer to eye level than low quality ones. Lower quality apples will be cheap and high quality will be a little bit expensive. Target all audiences or all kind of people, both the people who want to buy expensive ones and buying just from themselves. Maybe let's look at the kind of special one, making a festival thing, buying an apple from where you love on Valentine's Day campaign. Maybe that would be nice. Yeah, so this is shishoku is like eating the apples there and selling them there. That's also nice. Showing the sugar content there as well. Maybe nice. Yeah, I will share this information after taking away your names, and maybe you can have fun by looking at the different strategies of different people. As you saw quickly, it's very diverse, so, and nice. Okay. So some people just want to make money. That's fine as well. So any other questions? Yeah. Okay. No, I don't. It's not that I want to clarify. So okay, very important point. I want to explain to you about the final exam and stuff. Okay. So final exam. Oh yeah, maybe I can end the teams. So thank you very much for people from Taiwan. So the final exam thing is just for Japan. So thank you. Do you have any questions there? No?
No questions. Thank you.
Okay. Okay, great. Thank you very much. So I'm gonna close the teams here. Thank you. Okay, finals.